How are everyone doing? Good? Okay. Done. Today we'll be starting 2.2. And there isn't much to discuss here. So we'll most likely able to finish this and then go to chapter 3. Any question before we start? Any comment, concern, complaint? Just a reminder, I think tonight is 1.5, section 1.5 homework 2, if I'm not wrong. And they have extra credit.
What does that extra credit apply to?
Homework. Like few people, they didn't do few of the homework. And there are also people who lost homework points because they didn't show work. So when you do the homework, I expect you to follow the direction, means whatever direction says, follow that. Use that method to solve your question. And don't just give the answer, the final answer. You must show all the detailed work. In the work, maybe the numbers could be wrong, no problem if you get one or two things wrong, but I want to see detailed work. Any question?
What is the real application, right?
Exactly. So you have to complete, it doesn't mean just write, it says write ABC and you want to write DEF. No, you have to follow the direction, what the direction says. Okay, determinants. We already know how to find determinants of 2x2 matrix, 3x3 matrix, and today we are going to learn how to find the determinant of 4x4 matrix. But before that, there are some properties we want to discuss about the determinants. Two of them we already know, we discussed in our last class. The second one says, if your matrix has one complete row or one complete column full of zeros, then the determinant is automatically 0. You don't have to find the determinant. Also, another thing is if you have two identical rows or two identical columns, mean the same rows or same column more than once, then the determinant is 0. Now, the next three properties, three new properties is the determinant of A transpose is same as determinant of A. So if you know A transpose, then just find the determinant of A transpose. You don't have to switch back to find A. Now, about the multiplication, if you are multiplying A with an elementary matrix, any type of elementary matrix, either multiply on the left or right, doesn't matter. The determinant of the product is the product of the determinant. So determinant of elementary matrix times matrix A is determinant of E times determinant of A, which is same as determinant of A times E. So when you do matrix multiplication, the position of the multiplication doesn't matter. You can do EA or AE. However, this is not true for any other matrix. If we have any two random matrices A and B, determinant is same. The determinant of A times B is determinant of A times determinant of B. But it's not same as determinant of BA. Determinant of AB will not be same as determinant of BA because A times B is not same as B times A. Okay? Question? Now, there's a critical thinking question. We have the properties for multiplication. The determinant of the product is the product of the determinants. How about sum or addition? Sum or difference, sorry. Is this true? The determinant of sum or differences of two matrices is same as the differences or sum of the determinants? What do you think?
Go over what
You already forgot determinant. Determinant is a single number that tells us whether its inverse exists or not. So determinant, if the determinant is 0, inverse doesn't exist. If determinant is not 0, the inverse exists. So what do you think? We know there is a rule for product, but they didn't mention about the sum or addition. Any idea? No idea. Nobody has any idea. Well, as long as you can come up with one counter example that this is false, this is false. Can you think of a counter example that this is not true? Can you find two matrices, find their two individual determinants, and then find the sum of the two matrices, and then find the new determinants? Hi, Lon.
I was thinking making determinant A to be 0 somehow, and then B is not 0. So determinant A plus B would be something non-zero, but determinant A plus determinant B would be determinant B.
So if determinant of A is 0, but determinant of B is, let's say 1, let's say 2, then we have determinant of A plus B is 0 plus 2, which is 2. But how about A plus B?
Give an example of what A plus B would be.
Otherwise, how do you find the determinant of that A plus B matrix? Let's take any matrix. Elvin, what do you think? Okay, let's say, so let me, your idea is okay, but let me use this one now. We don't know. Okay, 1, 2, 3, 4. Let's do easy ones. And let's say B. Any idea for B? Let's pick a random thing, anything. -1, 0, 2, -3. Then we have determinant of A is the right diagonal minus the left diagonal. So 4 times 1 is 4, minus 3 times 2 is 6, which is -2. Then determinant of B, again, the right diagonal is 3 times 1, 3, minus the left diagonal 0. 3 minus 0, which is 3. So we want to see whether the determinant of AB will be -2 plus 3, which is 1. Is this true? So let's see what is A plus B. What's the sum of the matrices A plus B? Do you remember how to add matrices? Shivu? 0, 2, 5, 1. So what's the determinant of A plus B? Right minus left. 0 minus 10, which is -9. So is this true? The determinant of A plus B is -9? No, right? Determinant of A is -2, determinant of B is 3. So we assumed A plus B should be 1, but what did you find? Determinant of A plus B is not 1, it's -9. So, is this true or not true? It's false. Guess what? I'm going to ask this type of question in this exam. What's the determinant of the product and what's the determinant of the sum or difference? I mean, I'm gonna ask, is this true? And this statement, or is this true? And then the multiplication statement. If it's not true, show an example, counter example. Okay. That's why they didn't have this property, because it's not true. The next one, determinant of A inverse is 1 over determinant of A. Any idea how can you prove that? So if you take the inverse matrix and then we take its determinant, this is same as it's reciprocal of the determinant of the original matrix. Who has some idea how do you start this question? Proof. Any idea? Let me give you a hint. We all know that A times A inverse is what? What is any matrix times its inverse? Identity matrix. Good. So we are going to start from here. A times A inverse is identity. And now what can we do? Still no idea? Okay. What if we apply the determinant on both sides? Determinant of A times A inverse. Determinant of I. How about now? Any idea? Alvin? We cannot divide. I know, but here, if you divide, what's the point of finding the determinant?
A, the determinant of A times the inverse of A, determinant of A times.
So it's the divides distribution. I thought you mean divide. So distribute. We have determinant of A times determinant of A inverse. So we use the property. Determinant of the product is a product of the determinants. How about the right side? What's the determinant of any identity matrix? 1. Good job. Identity matrix is a diagonal matrix. What's the determinant of a diagonal matrix? Do you remember? Determinant of a diagonal matrix is, or any triangular matrix is, it's the product of the elements on the diagonal. So 1, 0, 0, 1, it has diagonal 1, 1. So determinant of 1, 0, 0, 1 or 1, 0, 0, 0, 0, 1, it doesn't matter which identity matrix is right. The diagonal has all element 1, so the product is 1. And now, as Elvin suggested, all you have to do is divide both sides by determinant of A. So we get determinant of A inverse is a reciprocal of determinant of A. The fun proof. As long as the determinant of, if determinant of A is 0, then the inverse doesn't exist. So this is true for all A, because the inverse has to exist. So determinant is not 0. Question?
That one, zero minus negative 9.
It's not 0 minus 10 is negative 9, yeah. How do you get 0? It's the right diagonal, which is 0 times 1, 0, minus the left diagonal, which is 5 times 2, 10. So 0 minus 10 is negative 9. It's a determinant.
Negative 10.
Also -10. Oh man, come on. Thank you. You know, even though I have 0, but in my mind I was thinking it's 1. What's wrong? Be confident. Thank you. Yeah, we have 0, but I was thinking 1 minus 10. Mm-hmm. Okay, the next thing, let me erase. I don't have to erase that. Can I flip my page twice? I guess I'm copying this one. Huh? So how do you find the determinant of 4x4 matrix? There are three methods. The first one is using cofactor expansion, which one is like you take one full row or one full column and then expand your matrix around that row or that column. For example, here they decided to expand around first column. So you take first element of the first column. As a result, you don't use the first row or first column, and you multiply by the determinant of the 3x3 smaller matrix. And then you have to remember your position. The first one is positive, then negative, then positive, then negative. Once you take the first element, multiply the determinant of the smaller 3x3, then you go to the next element. The next element is minus that element. As a result, you cannot use this or that. So this times the first row, third row, and the fourth row. 8 to 1 elements, and the first row, third row, and fourth row. Determinant of the 3x3 matrix of that 3x3 matrix. And then you go to the next element, which is the third element in the first column, and it has plus sign. So plus if1, since you're using this, so you cannot use the third row or the first column. So you left to a first, second, and fourth column. The first, second, and fourth column will give you a 3x3 matrix. You take the determinant of that. And lastly, you subtract. Let me change the color to blue. You take the last element, which is minus. As a result, you cannot use the fourth row or the first column. So you have column 1, row 2, row 3. So 3x3 matrix, you take the determinant of that. This is a longer process, but this is the formal way of finding determinant of any square matrix. You don't have to go column wise, you can go row wise also. You can pick any row or any column and do the same thing. Whatever row or whatever column you are using, you cannot use that row or that column, and then you take the rest 3x3. However, we don't always have to use this method, or at least you don't have to use it 4 times. We can only use 1 time if you expand around the row or the column which has the highest number of zeros. So it's like inspection. It's finding determinant by inspection. What does inspection mean? It means first you observe your matrix and see which row or which column has the most zero. So in this matrix, which row or which column has the most zero? Column 1. So we are going to expand around this column. In this column, we have 3 zeros. That means we are going to have 3 zeros for 3 cofactors. Only the non-zero entry will be the last one. And the position for that one, the first one is plus, minus, plus, minus. So this has a position -2. So we do -2 times. Now, since we are expanding around the first column, so we cannot use the fourth row. So we left with 2, 3, 0, 4, 5, 0, 1, 0, 3. So we are going to multiply by the determinant of that 3 by 3 matrix. But again, this 3 by 3 matrix, also we can find the determinant by inspection. Which column or which row has most zeros in this new? Third one. So if you expand around this 3, you don't have to use the third row or the third column. Third row or third column. And the position this time is plus, minus, plus, minus, plus. So we have plus 3. The first one was minus 2, and we are multiplying plus 3 by our matrix, the smaller matrix, 2, 3, 4, 5. And the determinant of the last one is easy because it's 2 by 2, so right diagonal minus the left diagonal. So our final answer here is -2 times +3 times the determinant of the 2 by 2. What's the determinant of the 2 by 2? If it's 2, 3, 4, 5 row-wise. Maisha. 2, 3, and 4, 5. Determinant. 2, 3, and 4, 5. Ten. 3 and 5 gives you 10, right?
2 and 5.
Oh, you have to multiply them. Okay. Multiply and then subtract. So right diagonal minus the left diagonal. Our right diagonal has 2, 5. And left diagonal has 3, 4. So what's the determinant? 10 minus 12. Which is -2, so I can simply write -2. So we have -2 times 3 times -2. Our final answer is? Go ahead, Maisha. Positive, right? -2 times 3 times -2. Positive. It's okay, no problem. Right? 2 times 3 is 6, 6 times 3 is 12, yeah. So I showed all the work, but you can actually do everything mentally. I mean, not everything. At least show me some work in the exam so that I can see you did it. You just didn't copy from anyone else. So equal. Question.
So you just like find which one is the one with the most zeros,
Mm-hmm.
and that's what you like either add or subtract.
Mm-hmm.
And then
What do you mean add or subtract?
to get the end.
Multiply. You always multiply. So 4 by 4 has only one row, so one column with most zeros. So we're going to, we did expand around that row or that column, not row, sorry, that column. So we have only 2 in that column that you're going to use. That means we left 3 by 3 matrix. And then we have to find the determinant of that 3 by 3 matrix. And you do the inspection again. As a result, we get a 2 by 2 matrix. So find the determinant of the 2 by 2 matrix again. And then you multiply the element with the most zeros times determinant of the 3 by 3 times the determinant of the 2 by 2. All of them are multiplication. And when you do find the determinant, the element, make sure you keep the position, the sign of the position. The first position is always positive, and then the sign alternate. Plus, minus, plus, minus, plus, minus. And when you go to the new matrix, the position, the sign starts again from the first position. So you cannot take the sign of this, the 4 by 4 matrix, to find a determinant for a 3 by 3 matrix. Every matrix you get a new position. The first position always starts from plus. Start with plus. However, if you find that your matrix has neither zeros or no, you don't want to find all these cofactors again and again and again, then there is another method. It's called is limited operation. I forgot. Do they have a name or not? It can convert your matrix into a diagonal matrix, so not diagonal, a triangular matrix, or you can convert one row or one column or two rows or two columns with most zeros so that you can use inspection method. Okay, either you can convert into a triangular matrix or make at least two rows or two columns with most zeros. The one column has to have 3 zeros, the other column has to have 2 zeros. Then we can use inspection methods easily. And when you use row operation, you're allowed to use the 3 operations. Swap 2 rows, multiply by a non-zero constant, and add 2 rows with multiplying by a constant. Maisha. Diagonal matrix has only non-zero element in the diagonal, and everything else has 0. Unit means 1. Diagonal has to have 1, but diagonal means it could be any number. And we can have 1 or 2 zeros, but everything else that is not on the diagonal must be 0. A diagonal matrix could be 1, 0, 0, 2. It's a diagonal matrix because 1 and 2 are on the diagonal and the other 2 are zeros. 1, 0, 1, 0. It's not a diagonal matrix because you have 1 that is on the non-diagonal position. All the elements on the non-diagonal position must be 0 to have a diagonal matrix. However, if you're thinking about triangular matrix, then you can have numbers below the diagonal or above the diagonal. But either below or above, all of the element has to be 0.
So a diagonal matrix is an upper triangular or lower triangular?
Exactly. Diagonal is both.
Both?
Yep.
So only the numbers on the diagonal are non-zero.
So if you consider it as a lower triangular, then it's a lower triangular. If you want to consider the upper triangular, then it's upper triangular. Okay, now for you, I have an example, a 4x4, find the determinants. You can use whatever method you like. You can use the cofactor expansion, or you can use row echelon form to convert this into a diagonal, not diagonal, a triangular matrix. So the non-zero here, and here you have numbers, and this is 0. Or if you want, you can do the other way around, no problem. So this is one method. Or if you want, you can put 0, 0, 0, 0 number, and then probably 0, 0 number. Okay, 2 choices. I mean, 3 choices you have.
Can we use both?
Sure. Wait, what do you mean both?
Like we change some of them? Make it easier for the other one.
Try it. So you can convert into, so this one already has a 0. So if you want, you can make these 2 zeros. And then when you do these 2 zeros, maybe you can make other 2 elements 0 in any other rows or any other column. So you want to get as many zeros as possible. This is one choice. If you have many zeros, then you can use inspection method. Or you can convert this into a triangular matrix. It means either above the diagonal or below the diagonal, you have strictly zeros. No other numbers besides zeros. Okay, Maisha.
So when you find the determinant of a 3 by 3 or
Mhm.
4 by 4 with the diagonals, can you use that to?
You can if you want to use diagonal, then you have to be a triangular matrix. So you have to convert your 3 by 3 or 4 by 4 into a triangular matrix. It means above the diagonal or below the diagonal, all the entries must be zero.
Find the inverse of our 2 by 2 includes a determinant, right? So can you use the determinant for all the other matrices too?
To find the inverse, we must use determinant. That's why we look for determinant. It doesn't matter what type of matrix you're using, you're trying to find the inverse of, like 3 by 3, 4 by 4. If you want to find the inverse, you have to multiply the new matrix by the reciprocal of the determinant. So determinant is the first step to find the inverse. And now,
You don't just use the identifiers?
that's a different method. If you want to use the inverse method, then you need to find the determinant. But if you don't like the inverse method, then you can use the identity method. So you're talking about a different method. So go ahead, enjoy. And if you're done, then I have another question for you, which is simpler. It says, we have a 3 by 3 matrix. For what number of C, this matrix will be singular? What does singular mean? Maisha.
But that, it's not invertible.
Good. And how do you know something is not invertible?
No, the candidates where the extended is, then the diagonal has to have 0.
Nope. The determinant cannot be zero. Singular means determinant is zero, not only diagonal. You can have a matrix that is diagonal, not zeros, and the inverse is zero. Not the inverse, sorry, determinant is zero. So singular means determinant is zero. Anytime you want to find whether a matrix is singular or not, just find the determinant. If the determinant is zero, it's a singular. If it's not a zero, then it's not a singular. Okay. Let me take the attendance and then I'll go pray. Okay, today is 10 what? 10:27. Thank you. 10:27. Brandon C. Joseph. Justin. Devron. Shibu here. Michelle. Jack. Jack, no laptop, please. Try doing these two examples. They'll be in the exam. Ashif. No. Darius. Winston. Abigail. Shane. Emily. Hanar. No. Christine. No. Edison. No. Maisha here. Brendan, not here. Shafal. Not here. Elvin here. Alexander. Not here. Shitila here. Wenchuan. And Kylon here. You can tell two neighbors while you do them. Wow, he's so cute.
No, platform, and then Yeah, so you only have two zeros. And when we have two zeros in that, that's how long we have. So if you enter the diagonal, then you have this, and then you want that to be zero. The only you can make it zero by using this column, this column. But then you do have this section.
So who is an answer? Alvin, Brandon. Okay. Brandon, which method you used? The cofactor or the inspection or the triangular? Inspection. Okay. So what did you do?
Zero and one, so I pulled the one out. And, I had
Oh, you're talking about B or A?
B, sorry.
B. Okay, no problem. I can do B first. It's okay. So you expand around the third row.
Yeah, I took the one that made a 2 by 2 matrix
Mm-hmm.
of, B1 minus one.
So 1 times, what do you have?
Minus one,
C minus 1.
wait.
You're doing this way, right? The right diagonal.
Yeah, so you multiply C minus negative 1 by C plus 1.
C minus 1, C plus 1.
And then you multiply negative 2, by C minus 1.
Negative 2 by C minus 1. Mm-hmm.
And then that becomes C squared plus 2C minus 3.
Really? These are two conjugates. C plus 1, C minus 1. Oh, you mean the entire thing, the final result. So
Yeah.
this one is C square minus 1.
Yeah.
And from here you get minus 2C plus 2. Right? If I'm not wrong.
Yes, but in parentheses, that way it becomes negative 2. And it's negative 2C also.
Negative 2C. And then we have negative 2 times negative 1. Plus, minus, plus, minus, plus. So 1 is plus, and then you're taking the right diagonal, which is C plus 1, C minus 1. Minus the, oh, negative 2, I didn't see negative 2. Negative 2 times C minus 1. So negative is positive 2C. Positive 2 means negative 2. Right? So C squared plus 2C minus 3. So this is the determinant of this matrix. Let's say this is A. A equals. And then what did you do with this determinant?
Then it's different C plus 3, C minus 1.
C plus 3, C minus 1. So you factored negative 3 into positive 3 and negative 1, and C squared into C and C.
That's the value C can be negative and positive.
You must set it equals to 0 first, right?
Sorry?
Set it equals to 0 first.
Oh, yes. You guys equal to 0, and then you do C
Negative 3.
0 factor 3.
Mm-hmm. Okay, I was doing shortcut. Let me do it the right way. C plus 3 equals 0 gives us C is negative 3. And we have C minus 1, 0, that gives us C is 1. That means either when C is negative 3 or C is 1, this matrix doesn't have any inverse. So we want to avoid those two numbers. Anybody has anything different for B? No? Alvin, for A, which method you used? For factor. Mm-hmm. Wait. Let me write it down slowly. So you're taking the first one. So plus minus plus. Position is plus. So 2 times negative 2, 4, 4. So you cannot use this row or this column. So negative 2, 4, 4. Negative 1, 2, 1. 3, negative 3, 2. So you're not using the third row. Negative, sorry, 1, 1, negative 1, 2. Mm-hmm. So minus 1. So now you're here. So you're not using, let me change the colors. Third row. One, negative 1, 2. Negative 2, 4, 4. Negative 1, 2, 1. Yeah, I have space, so let me squeeze them here. Negative 2, negative 1, 3, 4, 2, negative 3. And 1, negative 2, 3. Negative 1, 4, negative 3. 1, negative 2, negative 1, negative 1, 4, 2. So I need an image. Okay. 2 times. So we are adding all these diagonals. Negative what? Negative 8 plus 12 plus 12. So subtracting, when you go to subtracting, you are going to the right diagonals. Minus 24, minus 6, plus 8. A lot. 8 minus 12 plus 12 minus 24 plus 12 minus 4. So you are subtracting these diagonals. So these are the green ones. And now minus 1 times 4 plus 4 minus 8 minus 8 minus 2. So again, these are the right diagonals you're subtracting.
That would be.
Negative 6? Okay. Took long, but the answer is correct. It is 14. See, it took so many calculations. So if you don't want to do so many calculations, you can do inspection. Gregory, right? Let me show you the inspection method.
Could you go back? I just want to finish copying it.
Yeah, let me insert a page, sorry. Sure, it's okay, take your time. So inspection method doesn't take that long, I believe. Inspection. One negative 122. 1 negative 122. Negative 2404. Negative 2404. Negative 12. Negative 31. 3 negative 312. 3 negative 312. Okay, so this is the original one. And what did you do, Gregory, for inspection method? Okay. Anybody did inspection but got 14? No? Okay, so what Gregory did, he converted all of these into zeros, right? So let's do that. Make all of these into zeros. So we need to change row 2. So row 2, the new row 2 will be old row 2 plus twice row 1. If you use 2 times row 1, the negative 2 will become 0. Row 3, the new one is the old row 3 plus row 1. If you add the first row and third row, the answer is 0. For row 4, it's current row 4 minus 3 times row 1. Now the left part. Okay, let me do it on the side. Row 2, negative 2404. 2 times row 1 is 2, negative 244. When we add, we get 0248. Then row 3 is negative 1 to negative 31. And if you add row 1, so 1, negative 1, 2, 2, we get 0, 1, negative 1, 3. Then row 4 is 3, negative 3, 1, 2. And 3 times row 1 is negative 3, positive 3, negative 6, negative 6. So we get 0, 0, negative 5, negative 4, right? So 1, negative 1, 2, 2. The new row 2 is 0, 2, 4, 8. New row 3 is 0, 1, negative 1, 8. Sorry, negative 1, 3. And last one is 0, 0, negative 5, negative 4. So this is our new matrix. And now if you want, you can make this 0. Or if you don't want, you can leave it alone. Let me just leave it alone. I'm going to use 3 by 3 matrix. So inspection. The inspection says use this. So don't use this row or this column. I mean this column or this row. So we have insert 1 times 248, 1, negative 1, 3, 0, negative 5, negative 4. 3 by 3. And then in this 3 by 3, we have this 0. We can just use this method. 2, 1, 0, 4, negative 1, negative 5. And get the diagonals. Right diagonals are yellow. and green diagonals are left diagonals are green. So 1 times 2 times -1, -2, -2 is -8, sorry, +8. Then we have 0, and lastly we have -40. So and then you're subtracting 0. 3 times 2 is 6. 6 times 5 is -40. Sorry, what I'm saying, -30. Did I make a mistake? 2 times 4 is 8, positive, and the next one is 0. Then we have -40. 8 times 0 is 0. We have 5 times 2, 10, 30, -30. And then we have -40. Definitely -16. Definitely I did something wrong. Somewhere I did something wrong, some calculation. Right? But it should be easier, okay? As long as you do them correctly, it should be easier. And the answer should be 14. It would be 14 if you get 10, 16. So you get 6 and 8. Yeah. If these are positive, no, if these are negative, 40 is negative, 30 is positive, and 16 is positive, or 16 is negative. We have 56 and 38. Something like that. I have my signs wrong somewhere. -5, -4. But you get the idea, right? So you have to practice inspection method or cofactor method. It doesn't matter which method you use. Whatever is easier for you, you can use that in your exam. So in the exam, I'm going to give one 4x4 matrix to find the determinant. I'm going to give one 3x3 matrix to find the inverse. And you already found, 2x2 is easier, so I'm going to skip 2x2. Any question? Somewhere something is wrong. Okay, wrong. Any question? Then we have homework on 2.1 and 2.2. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Oh, we already did B, so ignore that. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16. And the due date will be next week, Monday, midnight. So homework from 2.1 is question 2 AV, 3 CD, question number 5, 4 BCD. From 2.2 is C, question 1C, 2A, 3A CE, 4A, and 7 CD. And you'll have exam questions from these also. Okay. With this, we are done with chapter 2. And now chapter 3. Next week, Monday midnight.
Okay.
Chapter 3 is a little bit different, a little bit advanced. In chapter 3, we are going to talk about Euclidean vector space. And you wonder, what is that? So we are going to watch a little video now. So you'll have some idea. And then on our next class, we are going to talk a little bit more about that. And then we'll be done with 3.1.
Will the video be posted?
I'll post the link.
Yeah.
Wait. It's too fast. Normal.
So if you to the problem of itself, it's actually a vector here. See, probably speaking, there are some a little bit of ideas about that. We don't all physics perspective. Vectors are arrows in the case. In the direction it's pointing. But as long as those two facts are the same, the fundamental root of it all building block for linear algebra is the vector. So it's worth making sure that we're all on the same page about what exactly a vector is. You see, broadly speaking, there are three distinct but related ideas about vectors.
Give me 1 second, I forgot to share sound. Share. No, don't share.
Which I'll call the physics student perspective. There are three same-page building blocks. The fundamental, root of it all building block for linear algebra is the vector. So it's worth making sure that we're all on the same page about what exactly a vector is. You see, broadly speaking, there are three distinct but related ideas about vectors, which I'll call the physics student perspective, the computer science student perspective, and the mathematician's perspective. The physics student perspective is that vectors are arrows pointing in space. What defines a given vector is its length and the direction it's pointing. But as long as those two facts are the same, you can move it all around and it's still the same vector. Vectors that live in the flat plane are two-dimensional, and those sitting in broader space that you and I live in are three-dimensional. The computer science perspective is that vectors are ordered lists of numbers. For example, let's say you were doing some analytics about house prices, and the only features you cared about were square footage and price. You might model each house with a pair of numbers, the first indicating square footage and the second indicating price. Notice the order matters here. In the lingo, you'd be modeling houses as two-dimensional vectors, where in this context, vector is pretty much just a fancy word for list, and what makes it two-dimensional is the fact that the length of that list is 2. The mathematician, on the other hand, seeks to generalize both these views, basically saying that a vector can be anything where there's a sensible notion of adding two vectors and multiplying a vector by a number, operations that I'll talk about later on in this video. The details of this view are rather abstract, and I actually think it's healthy to ignore it until the last video of this series, favoring a more concrete setting in the interim. But the reason I bring it up here is that it hints at the fact that the ideas of vector addition and multiplication by numbers will play an important role throughout linear algebra. But before I talk about those operations, let's just settle in on a specific thought to have in mind when I say the word vector. Given the geometric focus that I'm shooting for here, whenever I introduce a new topic involving vectors, I want you to first think about an arrow, and specifically, think about that arrow inside a coordinate system, like the xy plane, with its tail sitting at the origin. This is a little bit different from the physics student perspective, where vectors can freely sit anywhere they want in space. In linear algebra, it's almost always the case that your vector will be rooted at the origin. Then, once you understand a new concept in the context of arrows in space, we'll translate it over to the list of numbers point of view, which we can do by considering the coordinates of the vector. Now, while I'm sure that many of you are already familiar with this coordinate system, it's worth walking through explicitly, since this is where all of the important back and forth happens between the two perspectives of linear algebra. Focusing our attention on two dimensions for the moment, you have a horizontal line, called the x-axis, and a vertical line, called the y-axis. The place where they intersect is called the origin, which you should think of as the center of space and the root of all vectors. After choosing an arbitrary length to represent 1, you make tick marks on each axis to represent this distance. When I want to convey the idea of 2D space as a whole, which you'll see comes up a lot in these videos, I'll extend these tick marks to make grid lines, but right now they'll actually get a little bit in the way. The coordinates of a vector is a pair of numbers that basically gives instructions for how to get from the tail of that vector at the origin to its tip. The first number tells you how far to walk along the x-axis, positive numbers indicating rightward motion, negative numbers indicating leftward motion, and the second number tells you how far to walk parallel to the y-axis after that, positive numbers indicating upward motion, and negative numbers indicating downward motion. To distinguish vectors from points, the convention is to write this pair of numbers vertically with square brackets around them. Every pair of numbers gives you one and only one vector, and every vector is associated with one and only one pair of numbers. What about in 3 dimensions? Well, you add a
So when you write a point, we write x first and then comma y. That's the point. But for a vector, it's the same thing, but we write column-wise as a column matrix. And at that point, we draw a line from the 0, 0 to that number, and that's a vector. Okay. So vector is a point, but vector has direction.
the third axis,
and
called the
magnitude.
z-axis, which is perpendicular to both the x and y axes. And in this case, each vector is associated with an ordered triplet of numbers. The first tells you how far to move along the x-axis, the second tells you how far to move parallel to the y-axis, and the third one tells you how far to then move parallel to this new z-axis. Every triplet of numbers gives you one unique vector in space, and every vector in space gives you exactly one triplet of numbers. All right, so back to vector addition and multiplication by numbers. After all, every topic in linear algebra is going to center around these two operations. Luckily, each one's pretty straightforward to define. Let's say we have two vectors, one pointing up and a little to the right, and the other one pointing right and down a bit. To add these two vectors, move the second one so that its tail sits at the tip of the first one. Then, if you draw a new vector from the tail of the first one to where the tip of the second one now sits, that new vector is their sum. This definition of addition, by the way, is pretty much the only time in linear algebra where we let vectors stray away from the origin. Now, why is this a reasonable thing to do? Why this definition of addition and not some other one? Well, the way I like to think about it is that each vector represents a certain movement, a step with a certain distance and direction in space. If you take a step along the first vector, then take a step in the direction and distance described by the second vector, the overall effect is just the same as if you moved along the sum of those two vectors to start with. You could think about this as an extension of how we think about adding numbers on a number line. One way that we teach kids to think about this, say with 2 plus 5, is to think of moving 2 steps to the right, followed by another 5 steps to the right. The overall effect is the same as if you just took 7 steps to the right. In fact, let's see how vector addition looks numerically. The first vector here has coordinates 1, 2. And the second one has coordinates 3, -1. When you take the vector sum using this tip-to-tail method, you can think of a 4-step path from the origin to the tip of the second vector. Walk 1 to the right, then 2 up, then 3 to the right, then 1 down. Reorganizing these steps so that you first do all of the rightward motion, then do all the vertical motion, you can read it as saying, first move 1 plus 3 to the right, then move 2 minus 1 up. So the new vector has coordinates 1 plus 3 and 2 plus -1. In general, vector addition in this list of numbers conception looks like matching up their terms and adding each one together. The other fundamental vector operation is multiplication by a number. Now this is best understood just by looking at a few examples. If you take the number 2 and multiply it by a given vector, it means you stretch out that vector so that it's 2 times as long as when you started. If you multiply that vector by, say, 1/3, it means you squish it down so that it's 1/3 the original length. When you multiply it by a negative number, like -1.8, then the vector first gets flipped around, then stretched out by that factor of 1.8. This process of stretching or squishing or sometimes reversing the direction of a vector is called scaling. And whenever you catch a number, like 2 or 1/3 or -1.8, acting like this, scaling some vector, you call it a scalar. In fact, throughout linear algebra, one of the main things that numbers do is scale vectors, so it's common to use the word scalar pretty much interchangeably with the word number. Numerically, stretching out a vector by a factor of, say, 2, corresponds with multiplying each of its components by that factor, 2. So in the conception of vectors as lists of numbers, multiplying a given vector by a scalar means multiplying each one of those components by that scalar. You'll see in the following videos what I mean when I say that linear algebra topics tend to revolve around these two fundamental operations, vector addition and scalar multiplication. And I'll talk more in the last video about how and why the mathematician thinks only about these operations, independent and abstracted away from however you choose to represent vectors. In truth, It doesn't matter whether you think about vectors as fundamentally being arrows in space, like I'm suggesting you do, that happen to have a nice numerical representation, or fundamentally as lists of numbers that happen to have a nice geometric interpretation. The usefulness of linear algebra has less to do with either one of these views than it does with the ability to translate back and forth between them. It gives the data analyst a nice way to conceptualize many lists of numbers in a visual way, which can seriously clarify patterns in data and give a global view of what certain operations do. And on the flip side, it gives people like physicists and computer graphics programmers a language to describe space and the manipulation of space using numbers that can be crunched and run through a computer. When I do mathy animations, for example, I start by thinking about what's actually going on in space and then get the computer to represent things numerically, thereby figuring out where to place the pixels on the screen. And doing that usually relies on a lot of linear algebra understanding.
So that's the main concept of chapter 3. You are going to work with vectors, and vectors, the difference between numbers and vectors is that numbers written as a point format, but vectors written as a matrix format. Okay, so we are going to see each other again Wednesday in person. Have a good night. Be safe. See you again. Bye.